Welcome back. Section 4, Predicates and Quantifiers. Introduction. In this section, we encounter a powerful type of logic called predicate logic. Predicate logic can be used to express the meaning of a wide range of statements in mathematics and computer science. For example, in the statement x greater than 5, the predicate is greater than 5. That part is the predicate. Let p of x denote the statement x greater than 5 and call px the propositional function of p at x, where p is the predicate is greater than 5. Note, p of 6 is true while p of 3 is false, because 3 greater than 5 is false. 6 greater than 5 is true. So px is a propositional function. What does that mean? For varying values of x, p of x is a proposition. It is true or false. Okay, so it has a truth value. We can also have statements that involve more than one variable. For example, q of xy. So q is a function in two variables. This be the statement x equals y plus 5. Here q is the predicate, xy are the variables. We see that q of 2, 3 is false. Why? 2 equals 3 plus 5, that's false. But q of 8, 3 is true. 8 equals 3 plus 5, that is true. Here is another example. A of CP is the statement computer C is connected to printer P. If Math1 is connected to printer P1, then A Math1 P1 is true. On the other hand, if computer Math2 is not connected to printer P1, then A Math2 P1 is false. Let R x y z be x plus y equals z squared be a propositional function. Determine the truth values of R101 and R negative 110. Let's understand this. X is 1, y is 0, z is 1. 1 plus 0, that's 1, and z squared is this 1 squared, that's also 1. So it's equal. So R101 is true. What about R of negative 110? Well, negative 1 plus 1 is 0. 0 squared is also 0. So this is also true. So you can look at a propositional function and determine for various values whether what the outcome is, whether you are true or false at those values. In general, a statement involving n variables x1 through xn may be denoted by p of x1 through xn. A statement of the form p of x1 through xn is the value of the propositional function p at the n tuple x1 through xn. P is called an n-place predicate or a n-ary predicate. Okay, so this propositional function p, which takes n variables, is called an n-place predicate or an n-ary predicate. In computer programs, we use predicates. An example, if x is less than 0, then x is incremented by 1. So x is assigned x plus 1. Note, this example states that if x were negative, then we need to increment x by 1. The predicate being less than 0. That's the predicate. Preconditions and postconditions. Predicates are used to establish the correctness of computer programs. The statements that describe valid input are known as preconditions. Conditions that the output should satisfy when the program has run are known as postconditions. For example, consider the following program. Temp is assigned X. X is assigned Y. Y is assigned temp. So what does this program do? It interchanges the values stored in X and Y. So whatever value was stored in X is stored in a temporary variable. X in turn receives the value that was stored in Y, and Y receives the value stored in temp, which was the value stored in an earlier X, earlier. So that's how X and Y interchange their values. Now, we want to see what happens when X is A and Y is B are sent as input. Ideally, the output should be X equals B, Y equals A. Thus, we use the predicate Pxy to be the statement X equals A and Y equals B. That's your precondition. The predicate Qxy being the statement X equals B, Y equals A is the postcondition. Postcondition is the condition the output should satisfy when the program has run. Now argue using the given precondition into the program, and the result should be the given postcondition as we just saw. Precondition is X is A, Y is B. So X is A, that A gets stored in temp. Y is B, so that B gets stored by this assignment in X. Now X has B value. Temp has A value that got assigned to Y. So Y has B value, Y has A value and X has B value. So postcondition is met. Quantifiers. Quantification expresses the extent to which a predicate is true over a range of elements. The words all, some, many, none, and few are used in quantifications. Note, while we can test a predicate on one set of assigned values, quantifiers allow us to understand a predicate over a range of elements. We will focus on two types of quantification. Universal quantification. Here the predicate is true for every element under consideration. On the other hand, there is the existential quantification. Here, an existence of one or more elements under consideration is specified, for which the predicate is true. The area of logic that deals with predicates and quantifiers is called predicate calculus. The universal quantifier. Many mathematical statements assert that a property is true for all values of a variable in a particular domain. Such a domain of discourse or the universe of discourse, or simply I missed something. Many mathematical, such a statement is expressed using universal quantification. For example, x squared is greater than or equal to 0 for all real numbers x, for all. So that is an example of universal quantifier. For example, we know that the square of a number is non-negative for all real numbers. We will see shortly how to see this as a logical statement. This should not be positive, it is non-negative. Okay. The universal quantification of Px for a particular domain is a proposition that asserts that Px is true for all values of x in this domain. Note that the domain specifies the specific values, possible values of the variable x. Domain must always be specified when a universal quantifier is used. Without it, the universal quantification of a statement is not defined. So let me come to this definition in our next video.